How much boiling water do you need to melt a 200-pound block of ice? Why would you freeze in space? Why does metal feel cold to the touch? What is an ideal gas? The answers all boil or freeze down to thermodynamics, which is the physics of thermal energy and heat flow. The concepts of heat and temperature are part of your daily life. Understanding the laws that govern the temperatures of things, how heat flows between them, and how the material and thermal properties depend on each other has not only furthered physicists' appreciation of the world and its workings, it has also led to technological and engineering advances. A structurally sound bridge, for example, depends on understanding the thermal expansion of any of the bridge's metal elements. The motor car works because of the thermal energy released from the combustion of gasoline and air. These and more are only possible with an understanding of the relationship between the materials and their thermal properties. What really is heat? When you touch a hot object, heat flows from the object to you, and your nerves record that fact. When you touch a cold object, heat flows from you to that object, and again, your nerves keep track of what's happening. Your nerves record why objects feel hot or cold, because heat flows from them to you or from you to them. To understand heat, you need to understand thermal energy. Thermal energy is the energy that a body has in the vibrations of its molecules, the energy stored in the internal molecular motion of an object. The temperature of a body usually increases with its thermal energy. When two bodies are brought into thermal contact, thermal energy is free to be exchanged between them. If no thermal energy flows between them, they are in thermal equilibrium. In other words, they are in a kind of balance. Two objects in thermal equilibrium are said to have the same temperature. If thermal energy does flow between them, an object at a higher temperature is in thermal contact with an object at a lower temperature, and the thermal energy flows from the hotter body to the cooler one. They are not in thermal equilibrium. In physics, heat is thermal energy that flows from objects of higher temperatures to objects of lower temperatures. The unit of this energy in the MKS system is the joule, or J, the same unit you use for other forms of energy and work. 1 calorie is defined as the amount of heat needed to raise the temperature of 1.0 gram of water to 1.0 degrees Celsius. So 1 calorie equals 4,186 joules. Nutritionists use the food energy term calorie, or capital C, to stand for 1,000 calories. 1.0 kilocalorie, or kcal, so 1.0 calorie equals 4,186 joules. Engineers use another unit of measurement as well, the British thermal unit, or BTU. 1 BTU is the amount of heat needed to raise 1 pound of water 1.0 degrees Fahrenheit. To convert, you can use the relation 1 British thermal unit equals 1,055 joules. The following equation relates the amount of heat needed to raise an object's temperature to the change in temperature and the amount of mass involved. Q equals Cm delta T. Here, Q is the amount of heat energy involved, measured in joules if you're using the MKS system. M is the mass, and delta T is the change in temperature, and C is the constant called the specific heat capacity, which is measured in joules per kilogram degrees Celsius, or J / kilograms times degrees Celsius. You can use the heat equation to find how temperature changes when you mix liquids of different temperatures. Suppose you have 45 grams of coffee in your cup, but it cooled while you were figuring out the coffee's specific heat. You call over your host. The coffee is just 45 degrees Celsius, but you like it at 65 degrees Celsius specific heat. So the host gets up to pour some more. Just a minute, you say. The coffee in the pot is 95 degrees Celsius. Wait until I calculate exactly how much you need to pour. The following equation represents the heat lost by the new mass of coffee, M1. And here's the heat gained by the existing coffee, mass M2. Assuming you have a super insulating coffee mug, no energy leaves the system to the outside, and because energy cannot be created or destroyed, energy is conserved within such a closed system. Therefore, the heat lost by the new coffee is the heat that the existing coffee gains. So, therefore, you can say the following. Dividing both sides by the specific heat capacity C and plugging in the numbers gives you the following. There you go, folks. You need 0.03 kilograms or 30 grams. Satisfied, you put away your calculator and say, give me exactly 30 grams of that coffee.